Okay, so today we're going to introduce our first new graph shape now that we've talked a bit more generally about transformations. So we'll talk first of all about that basic shape and then look at how we apply those transformations that we talked about in our previous lesson to this shape. Just let me have a look, just adjust my pen width, sorry, I should have done this before I started recording. Okay, so the curve produced by the rule y equals 1 over x. So this is the new function we're interested in. Okay, y equals 1 over x. The curve that we get when we sketch that graph is called a rectangular hyperbola. Commonly we can just refer to it as a hyperbola. I'll talk about why in particular this is a rectangular hyperbola in a second once we've talked about some of the features. So this is the graph of y equals 1 on x. Okay, and we could plot this graph just by looking at points. Okay, for example, when x is equal to 1, y is equal to 1 over 1, so that is 1. So we go through the point 1, 1. When x is equal to 2, y is equal to 1 over 2, 1 half. When x is equal to 3, y equals 1 over 3, 1 third. When x is equal to 4, y is equal to 1 over 4, 1 quarter, 1 fifth, 1 sixth, 1 seventh, etc. Okay? So as x gets bigger and bigger and bigger, the value of y is getting smaller and smaller and smaller. What's important here though is it's never going to equal 0. When x is equal to 10 billion, y will be 1 over 10 billion. It will be tiny, but it's still not 0. Okay? So this is never going to equal 0. And so we get a feature of this graph we'll talk about in a second. Let's have a think. I'll come back to the middle in a minute. When x equals negative 1, y equals 1 divided by negative 1, which is negative 1. So we go through the point negative 1, negative 1. When x equals negative 2, y is 1 divided by negative 2, so that's negative 1 half. When x equals negative 3, y is 1 divided by negative 3, which is negative 1 third. When x equals negative 4, y is 1 divided by negative 4, which is negative a quarter, negative a fifth, negative a sixth, negative a seventh, etc. So again, as x becomes more and more negative, the value of y is getting closer and closer and closer to 0. Okay, so we actually have a special feature of this graph. The x-axis is called something special. It's called an asymptote. You'll see this word written down underneath the graph here. An asymptote is a line that a graph approaches without ever reaching it. It's an important feature of the graph. Okay, the x-axis here, which has equation y equals 0, is a line that the graph gets closer and closer and closer to, but never approaches. Okay, that's going to be a really important feature of this graph. Let's go back to thinking about the equation, because I skipped over some bits here. Let's think about, for example, when x equals 1 half. When x equals 1 half, y is 1 divided by 1 half, which is 1 times by 2 over 1, so it's 2. When x equals 1 third, y is 1 divided by a third, which is 3. When x equals 1 quarter, y is 1 divided by a quarter, which is 4. When x equals 1 fifth, y is 1 divided by a fifth, which is 5. When x equals 1/100th, y is 1 divided by a hundredth, which is 100. Okay, so this graph gets bigger as we get closer and closer to x equals 0. This graph gets bigger and bigger and bigger and bigger. Okay, however, when x equals 0, 1 divided by 0 is undefined. So there is no y-intercept for this particular graph. Okay, if we have a look down on the negative side as well, when x is negative a half, 1 divided by negative half is negative 2. When x is negative a third, 1 divided by negative a third is negative 3, etc. So we get the same pattern happening. The graph is becoming more and more negative. When x is negative 1 on 100, the graph will equal negative 100. The y value will be negative 100. So the graph gets more and more negative as x gets smaller and smaller and smaller, or more and more positive as x gets, more and more negative as x gets closer and closer to 0 from below, more and more positive as x gets closer and closer to 0 from above. Okay, so we get this divergent behaviour where the graph heads off in two different directions. At x equals 0, the graph doesn't exist. So again, x equals 0, or the y-axis, is another asymptote. It's a line that the graph approaches. It gets closer and closer and closer to the further up that and down that graph we look, but it's never actually going to reach that point. So we have these two new features called asymptotes. Now let's get back to the fact that this particular graph is called a rectangular hyperbola, and that's because the two asymptotes defining this hyperbola are at right angles to each other. It's possible to have other hyperbolas where the asymptotes are not at right angles, for example, something like this, okay, that's a non-rectangular hyperbola, it's still a hyperbola. We won't be looking at those, we are just focused on rectangular hyperbolas, which are variations of the equation y equals 1 over x. Okay, so we have a new graph feature, asymptote. An asymptote is a line that the graph approaches without ever reaching. It is the limiting value of the graph, okay? So as x gets bigger and bigger and bigger, the limiting value of y is 0, but it never actually reaches 0. We can see the graph of y equals 1 over x has asymptotes at y equals 0, the x-axis, and x equals 0, the y-axis. Okay, so in graphs where the asymptotes are not the axes, and we'll have a look at that's going to happen fairly quickly, the asymptotes should be drawn as straight dashed lines. Okay, so we're going to draw a straight horizontal line in case of the horizontal asymptote, or a straight vertical line, but it's going to be a dashed line, and the graph will get closer and closer to that line but won't actually touch that line. I know I made this pen a bit thicker, but I'll leave it thick for now, but when we draw some graphs I'm going to make it thinner so I can be more precise. Your sketch needs to indicate your understanding of what an asymptote is. Okay, so it's really important that when you draw a graph with an asymptote, let me draw it a bit bigger here. Let's say I've got my asymptote happening here. It's really important that your graph shows that you understand asymptotic behavior. So your curve gets closer and closer and closer to that line, but it never actually touches that line. What you don't want to see is your curve accidentally touching the line, perhaps because you didn't sharpen your pencil enough and it's not very clear. You've completely undermined what an asymptote is by drawing that. You certainly don't want to accidentally cross over the line, okay? Now, it's possible for graphs to cross asymptotes, okay, because you can have something, for example, where the graph is asymptoting out this way, but we're not dealing with that for now. But certainly where you're heading off out into the area where your graph is getting closer and closer to the line, you shouldn't be veering towards it or touching it. The other thing you need to be careful of is that your graph shouldn't be parallel to the asymptote, sorry, because it needs to continue to approach it. It's really important that. And the last thing is obviously that your graph shouldn't be veering away from the asymptote at any point. Okay, it's really important that your graph shape reflects your understanding of what an asymptote is. A number of years ago now I marked exams for VCAR, and in that year there was a hyperbola as a graph that the Year 12 students had to draw in their exam, and they were very, very strict on graph shape, in particular around the asymptotic behaviour. If it touched the asymptote, if it veered away from the asymptote, if it was parallel from the asymptote, if it crossed the asymptote, you will have lost the mark for shape. So it's really important that you take care with that and that you get used to taking care with that sort of thing from now. Don't expect to turn up to that exam in 18 months' time and all of a sudden be able to work with that level of precision. It's practiced and learned. As always, X and Y intercepts should always be labelled, and if there are no intercepts then we should have at least one point labelled on the graph to give us a sense of the dilation happening with the graph. We'll talk more about that as we work through some examples. Let's go back up here. So we've talked about what would happen if the asymptotes are not at the axes. So let's think about the three transformations that we talked about yesterday. Dilation, reflection, and translation. I want you to take a minute to think about which of these three transformations is going to possibly change where the asymptote is. So remember, dilation is about multiplying all of the y values by a number. Okay, so when we do that, y equals 0 isn't going to go anywhere. When we stretch that graph away from the x-axis, okay, it might get further away, but it's actually not going to change where the asymptote is. Reflection, okay, so that's going to reflect in the x-axis. The graph will go down here and up here, okay? It's still not going to change where the asymptote is. The things that are going to change are translations. If we were to take this graph and translate it up by 2, we also need to translate with it the asymptote. Okay, so translating it up by 2, the asymptote would go up here, not y equals 0 anymore, y equals 2. So we draw it as a straight dashed line labelled with its equation, y equals 2. And then you would have your hyperbola, I'm not being very precise with the grid here, but just a vague shape, happening up here. Again, we could have translations left and right. And in that case, it wouldn't be the horizontal translation that would move, it would be the vertical, the horizontal asymptote that moved, it would be the vertical asymptote. So let's say we move this graph to the left by 2. So now my asymptote is at x equals -2, and again, I'm not being precise with my intercepts and other things, but just a general sense of the shape would happen over here. Labelling the asymptote, x equals -2. So dashed straight line with its equation. If you're not very good at drawing straight lines without a ruler, use a ruler. Use the edge of your CAS. Okay? Use some sort of straight edge to give you a straight asymptote. So translations are going to be the ones that move where those asymptotes are. Okay, so let's start to combine together this equation with our known transformations. Okay, so we know that when we dilate by a factor of a from the x-axis, we take our function f of x and we multiply it by a. Okay, so in this case, what we're looking at here is f of x is 1 over x. We're looking at that special case. So we're going to get a times f of x, a times 1 over x, which we know we can write as a over x. Okay, so dilation of the hyperbola by a factor of a from the x-axis would, in the equation, look like y equals a over x. Reflection in the x-axis, again we make the whole function negative, or -1 times the function. Okay, so that's just going to be -1 on x, which is the same as -1 over x, which is the same as 1 over -x. They're all the same thing. Okay, so reflecting in the x-axis. Translation to the right by h units. Okay, so this is where we replace the x part of the function with x minus h. Okay, so inside the function becomes x minus h, therefore we replace just the x part of the function with x minus h. So our function is now going to be 1 over x minus h. Translation to the right by h units. Translation up by k units is where we add on after the function. So our function is 1 on x, and then we're going to add k onto that. Okay, so see the difference between those two translations. Left or right, inside the function, under the denominator of the fraction with the x is where you're going to see the plus or minus. Up or down, completely outside of the fraction, okay, is going to translate up or down. So then if we combine all those things together, we could have a over x minus h plus k. If a is negative, we'll get a reflection. A will do, otherwise dilate. Translation left or right from h, and translation up or down from k. So we're looking at that most general form of the hyperbola. Okay, so taking those, let's now draw some graphs. I'm just going to make my pen nib a bit narrower again so that I can be a bit more precise. Okay, sketch the graph of y equals -3 on x. We've got two things happening here. The negative, okay, which is giving us reflection in the x-axis. So think about what that means for this shape. Okay, so normally the shape goes up here in the first and the third quadrants. When we talk about graphs, we talk about the quadrants, 4 quadrants. When we reflect that in the x-axis, the section of the graph that was in the first quadrant is going to go down here into the 4th quadrant, and the section of the graph that was in the 3rd quadrant is going to come up into the 2nd quadrant. So we essentially get, you know, the shape graph happening in those 2 quadrants. We've also got dilation by factor 3 from the x-axis. Okay, so we haven't got any translations, which means our graph is not going to, our asymptotes are not going to move. So that means the x-axis remains an asymptote, the graph will not cross the x-axis, and the y-axis remains an asymptote, the graph will not cross the y-axis. Okay, so therefore we need another point, okay, on the graph because we don't have any x or y intercepts. So for example, we might just look at when x equals 1, we know that y is going to equal -3 over 1, so -3. Or you might look at when x is -1, would mean y equals -3 over -1, so it equals +3. And they will just at least give you some points on your graph so that you can tell that this graph is different from -1 over x or different from -10 over x. Okay, otherwise we don't have that information. So, axes, they're my asymptotes, so they're going to go nice and centrally. Anytime you draw a hyperbola, you need to draw the asymptotes in first, so in this case that's our axes. I'm going to have the point 1, 3, and I'm going to have the point, oh sorry, other way, 1, -3, and -1, +3, so let's get them sort of, let's get them sort of vaguely symmetrically happening, so our graph's a bit symmetric. and then we're going to draw in a hyperbola going through that point, approaching my x-axis. I had that little veer away at the end there. It's hard, it's slippery on the screen. Okay, and then again approaching my x-axis, but also approaching the y-axis. Don't forget you've got this point up here. It helps if you don't give yourself too big an axis, okay? Or if you don't draw the scale. So if I had instead, let me just draw a different line in a different colour. If I had instead marked the point 1, -3 here, it would have been, sorry, that's got to, if I'd marked 1, -3 here, it would have been very tough to accurately keep getting closer and closer to the x-axis all the way down here when I've got such a long way to go, okay? So it's also about being sensible about how you draw, how you scale your axis and where you put your points. Okay, so we're going to label this point 1, -3. We're going to label this point -1, +3. My asymptotes in this instance don't need to be labelled with an equation because they are the axes, but that's the only time when you don't need to. Okay, let's have a look at another example, number 2. Sorry, took a minute. Sketch the graph of y equals 1 over x plus 2, and then all of that plus 5. Okay, so inside the function here, that's my left or right translation. Outside the function here, that's my up or down translation. So we have got translation to the left by 2, and we've also got translation up by 5. So translating to the left by 2 is going to move the vertical asymptote. So the vertical asymptote will go from being at x equals 0 to x equals -2. And the translation up by 5 will move the horizontal asymptote, so it will go from being at y equals 0 to y equals 5. So these are my asymptotes. Okay, that's the most important place to start. You need to draw in the asymptotes first, so you've got structure within which to draw your graph. Let's just think about that. I'm going to draw myself some axes with those asymptotes. Okay, so, sorry, I should have moved this over. Okay, so I'm going to have, let's say 1, 2, let's say 1, 2, 3, 4, 5. Okay, so I'm going to draw in my vertical asymptote at x equals, sorry, I've got a bit crooked, didn't it? At x equals -2. And my horizontal asymptote at y equals 5. Some people attempted to mark that point to -2, 5 with coordinates. It's not a point on the graph, okay, it's not relevant. So we're not marking that point, we are labelling the straight lines, which are what's important, with their equations. Okay, so then we're thinking about, probably didn't scale my axes very well here, or I shouldn't have made my asymptote so far apart. Anyway, so our graph hasn't been reflected, which means our graph stays happening in the first and fourth quadrant. So it's going to happen up on the top right and down the top left relative to those asymptotes. Okay, so that's where my hyperbola is going to go. Before I'm going to draw it in, I'm actually going to calculate, because we're now going to cross the x-axis, probably, sorry, the y-axis somewhere here as my graph goes around here, and we're going to cross the x-axis somewhere here as my graph comes down here. So we need to actually calculate those points. And then let's draw in our graph. So my y-intercept, same for any other function, we let x equal 0, so we get y equals 1 over 0 plus 2, so just 2 plus 5, so it's half plus 5, that's 5.5, or 5 is 10 on 2, so it's 11 on 2. My x-intercept, we let y equal 0. Okay, let's take away 5. We need to get rid of the fraction. Let's multiply by x plus 2. Let's divide by -1/5. Sorry, I don't need those brackets anymore. X plus 2 equals, sorry, divide by -5. So x plus 2 equals -1/5. And so x is going to be -2 minus 1/5. That's -10/5 minus 1/5, so -11/5. Okay. So it's negative 2 1/5 and positive 5 1/2. So just thinking roughly where that's going to be. Now I'm not going to draw them in. I'm not going to mark them on before I draw the graph in. I've just got the sense of, okay, it's going to be at 5 1/2, so it's going to be roughly kind of there, and it's going to be at negative 2 1/5, so it's going to be closer to that asymptote. But if I don't actually hit those points, I don't want to have them perfectly labelled in there, right? So we're just going to sort of get a sense of, I'm aiming for roughly here, but I'm going to draw it first. Alright, trying not to sort of... Now, I probably haven't done myself any favours with such a long asymptote. I should have planned that a bit better. Okay, so, you know, think about actually, you know, not drawing that axis so much, only, you know, cutting it off there so that you don't have to get quite so close to the asymptote. Similarly, I probably haven't done myself any favours on the other side either. Okay, so asymptotic, getting closer and closer and closer and closer, quite close here, somewhere down there. Okay. So that is 0, 11 on 2, and that point is negative 11 on 5, 0. So because I've got intercepts, I don't need to find other arbitrary points on the graph. My intercepts are giving me a sense of dilation, and in this case there is no dilation other than 1, but you still need to be able to show that. You should be able to have enough information on your graph that someone could work out the equation of your graph, knowing that it's a hyperbola. Okay, number 3, sketch the graph of y equals negative x minus 4. Okay, so we've got the negative out the front, that is reflection in the x-axis. So that means relative to my asymptotes, my graph is going to go in the second and fourth quadrants. So it's going to be in those two quadrants. And then we've got x minus 4 underneath the denominator of the fraction. That is a translation to the right by 4. So that means we're going to have an asymptote when x equals 4. We're going to move that vertical asymptote across to when x equals 4. Alright, so let's have my y-axis, let's have my x-axis in the middle because that is the asymptote. I haven't moved that one. We're going to have x equals 4 for the translation to the right by 4. We've reflected the graph in the x-axis, so it is going to go this way here. So we're not going to cross the, reflected, yes, in the x-axis. We're not going to cross the x-axis, it's still the asymptote. We are, however, going to have a y-intercept, so we need to calculate that point. Okay, so the y-intercept, we let x equal 0, so negative 1 over negative 4, and so we've got positive 1/4. Okay. Alright, so we can just draw in our shape and then label that point with a quarter. Haven't got any other y values anywhere on the graph, so we don't need to worry about sort of relative scale. I'm going to try and get some symmetry to your shape. You'll get better at drawing these with practice, like any graph. So the y-intercept at 0, 1/4. So we've got at least 1 point, we've got our asymptotes, y equals 0, which we don't need to label with equation because it's the x-axis, and x equals negative 4 for the other one. Okay, example number 4. Which I think, no, we've got 2 more. Sketch the graph of y equals 1 over 3x minus 18. Okay, now this is interesting. We haven't seen a number down here, but let's have a think about how actually we could rewrite that. 1 over 3x is the same as 1/3 times 1 on x. So we can think about this as being our a times f of x, and then, you know, plus k. So we've got our dilation by a factor of 1/3 from the x-axis, so the graph's going to get squashed down closer to the x-axis, and then we've got our translation down by 18 units. Okay. So my horizontal asymptote is going to be down at y equals negative 18, and we've got the dilation happening. So let's just think a little bit about those asymptotes. So my vertical asymptote's not moving anywhere. My horizontal asymptote is going to be quite low down, so I'm going to draw my x-axis quite high up. Okay, so y equals negative 18. Okay, we haven't got any reflection, so our hyperbola is happening here and here, which means we're going to cross the x-axis somewhere here that we need to calculate. We will not cross the y-axis because it is an asymptote. Okay. Alright, so let's calculate our x-intercept, which is to let y equal 0. So 0 equals 1 on 3x minus 18. Let's add 18. Let's multiply by 3x. So 3 18s, 30, 40, sorry, not 48. 3 10s are 30 and 3 8s are 24. So 54 equals 54x equals 1. And so x equals 1 on 54. Okay, so very small x-intercept. Again, we don't have any other x scale, so it doesn't really matter where it goes, but we do want to give the sense that it's quite close to the y-axis. Alright, so we should be able to draw in our graph. Okay, and we're going to mark our x-intercept at 1 on 54, 0. We haven't got a y-intercept, but that's okay, we've got at least 1 point, and we've got both our asymptotes, y equals negative 18 and x equals 0. Okay, example 5, I think it's the last one. No, we've got one more. Example 5, sketch the graph of y equals 1 over 2x plus 1, showing all important features. Okay, now this is quite complicated in the way this has been given, and it doesn't fit our normal format where we don't want to see a number in here. We can interpret that in a different way, but I want us to think about how we can interpret it within the scope of what we already know. So we want to be able to write it as x plus or minus h and plus or minus k. We want to be able to not have a number in here. So if we think about how we can do that, we've got y equals 1 over, let's factor out that 2, so that's x plus a half, which means we can write this as 1/2 times 1 over x plus a half. Okay, so it is in the format that we can now understand. Our a value is half, dilation by half from the y-axis, from the x-axis, sorry. Dilation by a factor of half from the x-axis, and then our translation is to the left by 1/2. So we're going to have an asymptote at x equals negative a half. Alright, so again, let's think about drawing in our graph. Try and draw that straight. Okay, so my x-axis, sorry, my vertical asymptote is x equals negative 1/2. Alright, no reflections. We've got a dilation, but that will come into account when we work out the intercepts. So we know our graph is going to be here and here, so we're going to cross the y-axis somewhere here, but we won't be crossing the x-axis, so we need to work out a y-intercept. So that is letting x equal 0, 1 over 2 times 0 plus 1, so it's 1 on 1, which is just 1. Okay, so we want to draw in our hyperbola. Again, not done myself any favours with the big axes. Should have just drawn my half a bit further away. My asymptote of half a bit further away. Made life hard for myself putting it so close. And so we've got our graph, y-intercept at 0, 1, asymptote labelled. Okay, last one here, example 6. We want to first of all show that 5x plus 3 over x plus 1 is equal to negative 2 over x plus 1 plus 5, and hence sketch the graph. So in this format, we can see the transformations and we can sketch the graph. In this format, we can't. So we want to be able to use the fact that these two things are equal when we sketch the graph. So essentially, we are sketching the graph of y equals negative 2 over x plus 1 plus 5. But before we do that, we need to show that they are actually the same thing. Now, show that, again, let's talk a bit about this. We don't assume the two things are equal. We want to take one side of the equation and manipulate it to show that it gives the other side. Okay, we don't want to start by assuming that those two things are equal to each other. If we do that, we'll manipulate it and end up showing that 0 equals 0, which is completely unhelpful. It's just a true statement. So we're going to start with the left-hand side here, which is equal to 5x plus 3 all over x plus 1. Now, we're going to do a slightly sort of cheating technique here, not cheating, but what we want to look at is we want to go from a version of this equation that has x in the numerator to a version that doesn't have any x's in the numerator. That's the biggest issue. So we need to be able to cancel with the numerator and denominator, and the only way we can do that is with common factors. So the only way I'm going to be able to do that is if somehow I have x plus 1 up here that I can cancel down. I can break my fraction up and cancel down with the x plus 1 on the denominator. Okay, it's the only way I'm going to be able to cancel this fraction down. So this is the first thing that I write down then. Okay, I simply write what I want to happen. I want there to be an x plus 1 in the numerator. Now we focus on manipulating, in making sure that these two lines of our equation are equal. So in order for there to be a 5x, there'd have to be a 5 outside this bracket. So now my equation is 5x plus 5 all over x plus 1. But I don't want plus 5, I want plus 3. So I also need to take away 2. Now if I expand out that numerator, it is 5x plus 5 minus 2, so 5x plus 3. So these two lines are perfectly equal to each other. The advantage of rewriting it in this way is now I can split my fractions into two fractions. This is 5 times x plus 1 over x plus 1 minus 2 over x plus 1. Okay, and so now the left-hand fraction, the x plus 1's cancel down, and we get 5 minus 2 over x plus 1. So we get negative 2 over x plus 1 plus 5. Okay, which is the right-hand side. And so we have shown that algebraically we can convert the left-hand side of the equation so that it is equal to the right-hand side of the equation. It is technically possible to also do it in reverse, but it's sort of not quite what you're being asked to show. But if you were to start with the right-hand side, minus 2 over x plus 1 plus 5, common denominator, then you can add them together. You've got negative 2 plus 5 times x plus 1 all over x plus 1. Expand out your numerator, 5x plus 5. 5. And so you have got 5x plus 3 all over x plus 1, which is the left-hand side. Okay. Technically, either way is valid. I would say it's nicer to be starting with the right-hand side and making it equal to the left-hand side because that's sort of the direction you're being asked to show it. You're being asked to show that this ugly thing which we don't know how to graph is equal to this nicer thing that we do know how to graph. So you sort of want to start with that ugly thing that we don't know how to graph and show how to turn it into the nicer thing that we do know how to graph. Okay, so now that we've shown that these two things are equal, if we are trying to sketch the graph of y equals 5x plus 3 over x plus 1, we are being asked to sketch the graph of negative 2 over x plus 1 plus 5. Okay, so thinking about what's happening with this graph, this is reflected in the x-axis. So our graph shape relative to the asymptotes will be in the second and fourth quadrants. It is dilated by a factor of 2 from the x-axis. It is translated left 1 and up 5. So left 1 is going to make your asymptote x equals negative 1, and up 5 is going to make your asymptote y equals 5. We're going to cross both axes when we do that, but let's just get our axis drawn in so we can get a sense of what we're trying to do, and then we can find the x and y intercept. So I'm interested in my asymptotes first. X equals negative 1 and y equals 5. Just extend out this way a little. Got room for my x equals negative 1. Okay, there's my two asymptotes. My graph is in these two quadrants because of the reflection, so we're going to cross the x and y axes somewhere down here. So we need to actually calculate those two values first, and then we can draw in our graph. Alright, so the y-intercept, we'll let x equal 0. Now you can choose whether you want to use the original version of the equation, which might be nicer. If you let x equal 0 there, you're just going to have 3 over 1, so 3. It's simpler than in the other equation, up to you, although it's not difficult in either of them. Your x-intercept, probably easier to solve for x in the equation that's only got one x in it, so you probably go with this one. Now, negative fractions, let's just add the fraction onto the other side to avoid the double negatives. Let's multiply by x plus 1. Let's divide by 5. And then we need to take away 1. So x is 2/5 minus 1. Remembering 1 is 5/5. 2/5 take away 5/5 is negative 3/5. Okay, so it's important that you've got these points relatively in the right place compared to your asymptotes. So for example, you don't want your y-intercept to end up down here. It's at y equals 3, which is more than halfway to the asymptote. Okay, so it certainly should be somewhere in this vicinity up here. Okay, ideally you want to sort of be vaguely precise about it. Again, 3/5 is more than half. Negative 3/5, sorry, but it's more than half, so it's closer to the asymptote than it is to the y-axis. Okay, so making sure that we're sort of, vaguely have those happening in the right place. So perhaps give yourself some rough points that you're aiming for. Just going to start again. So that when you draw your graph in, you can sort of hit those points. Okay, so we've got, and then other part of the graph up here. Alright, so y-intercept at 0, 3, x-intercept at negative 3/5, 0. Okay, and there is your graph of the hyperbola. So it's a couple there for you to have a go at drawing.